All right, so gas laws. And let's see them one more time. The gas laws again. We've got a bunch. Boyle's, Charles's, Gay-Lussac's, combined, Dalton's, and the ideal gas law. All right, Boyle's. Let's grab a color that's hopefully easily seen on this. Boyle's is P1V1 equals P2V2. Charles's V1 over T1 equals V2 over T2. Gay-Lussac's P1 over T1 equals P2 over T2. Combined P1 V1 over T1 equals P2 V2 over T2. Dalton's PT, the total pressure, P1 plus P2 plus dot dot dot. Keep adding them. And the ideal, PV equals nRT. There you are for the gas laws. Now there are some things that you just want to remember and kind of keep it simple. You really, I guess here, let me grab this. You really only need to remember the last three, okay? Because Boyle's, Charles's, and the combine and Gay-Lussac's combine into this one. And again, if you don't have a change in any of those variables, if temperature remains constant, cross it out of your combined and use PV equals PV. All right, so you really only need to know that one. So you've got your, here if I highlight this, grab a highlighter. Oops, not a great highlighter, different color. These three, okay? So, but there you are. You really only need to remember those three. Another thing you really want to take a look at, and this is important, is that temperature must always be in Kelvin. Very important. You must always have your temperature in Kelvin. I'm a big fan. I don't like that red, so let's go to another color. Here's let's go to some, I think this purple will look okay. Okay. I'm a big fan of rewriting equations before you solve. For what you're looking for what you want, okay? So if you're solving for V2 in the combined gas law, rewrite the equation before you plug any numbers, and I think it's just helpful to do, okay? Then when it really comes down to it, it's using these equations, you know, remembering the 0.0821 atmosphere liters per mole Kelvin. Now notice I did mention that we always must have Kelvin for all of these temperatures. Here we must, because of course the constant tells us that, but I didn't mention we should know that the volume is in liters. You can use volume in milliliters, let's say, in your other ones, as long as they're the same. If V1 is in milliliters and V2 is in milliliters, they'll cancel. You can't use milliliters in the ideal gas law because the constant has liters in it. But there are your laws. That's a little bit about our gas laws. I have a little simulation. Let's see if this loads. Hope it does. This is from Phet. It's the University of Colorado. We'll see if it loads here. Simulation. So phetcolorado.edu. And this is a kind of a cool little simulation. I downloaded it earlier. Let's see if I can find it. Boy, I don't know where it is here. Let's just take a look. So let's just run this. Let's see if we can run this. Might take a second. Of course, there it is. And it's a cool simulation. You could certainly go to it. Again, it's phet.colorado.edu. There's a bunch of different simulations you can use. And they're cool. They're just simple little simulations that you can change some variables, adjust some things, and it kind of, you know, shows you how things work. So here's as you can see, a enclosed system. Notice I have a pressure gauge, it's not reading, a temperature, it's saying 0K, it's just getting ready for me to go, and some heat. Notice that this little dude over here is holding this outside. If I now put some gas in here, all right, I just pumped in some gas. You now see that my dude's going to start to move around a little bit. He might he doesn't do too much right now. He's strong enough to hold it. He's stepping low. Okay, my pressure is 0.5 atmospheres. Temperature 300 degrees Celsius. And notice this is kind of my pressure right here. If I add some heat, notice I'm going to fire it up. Let's go to 500K, or I'm almost at 600. Notice by increasing my temperature, I've increased my pressure. Why is that? The molecules are moving around a lot more fast, okay? So they're moving around fast, they're smashing up against the thing, all right? If I change my volume, I can make this guy slide this in and make the volume. So if I shrink my volume, look what happens to the temperature and the pressure. Decrease the volume is going to increase the temperature and increase the pressure. Okay, I'm at 2.7 for pressure, atmospheres, and 800 for a temperature. Let's increase my volume, and notice by increasing my volume, I'm decreasing my pressure, decreasing my temperature. Let's bring them back in. What if we put more? So this would be the ideal gas law. I'm putting more molecules. Look at how much trouble he's having to keep that. Oops, and my lid busts out. Too much pressure, temperature too hot, explodes out of it. It's a cool little simulation. You can see it on this PHET at colorado.edu. And there's a bunch of different simulations. That's gas loss. Hopefully you're comfortable with them now.